morning, students. So today's topic is code generation, but before that, you have to understand the concept of abstract syntax. The abstract syntax means that it is the tree. It is for the grammar for the tree. Though we want to unambiguous grammar to prevent conflicts, so when you write YAG grammar or any other grammar for the parsing, you have to avoid conflicts. So you are preferring unambiguous grammar. But unambiguous grammar can be useful to representing abstract syntax. For example, you know that this is a version of abstract syntax. This is called abstract syntax. So which is an ambiguous one. And you can see there's a subscript there. So in order to tell the difference, which part are you considering? So that is the difference of the abstract syntax. Regarding to abstract syntax, this is called a concrete syntax. So you may think about that. The concrete syntax is for parsing. So abstract syntax is for translating. So we are facing the code generation, which is actually translating something. So we have to consider abstract syntax. So just beware that abstract syntax it can be ambiguous. So the grammar for it is representing the abstract syntax tree. So you may consider that an abstract syntax is for representing AST. So you have to just take a look at the expression. So you may think that an expression can be an addition of 1 and 2. Okay, so you can see that it is a part of this form where this is the subpart of expression 1, and this is the subpart of expression 2. Okay, so the abstract syntax is essentially a pattern for AST. So this may be called, may be regarded as a pattern of an AST. So do you have any questions up to here? So just reminded that you are going to use abstract syntax, ambiguous grammar to handle your AST. That is the key. So if you are familiar to the abstract syntax, you can consider the code generation function as a semantic function. So don't worry about the word of semantics. So just it is a function. It is a normal procedure or function in C. So the functions in C, as you know, it is essentially procedure. But in your book, this is called, in your code, it is a function, but in your book, in your compiler book, this is called a semantic function. So you have to translate the syntax to generate a useful semantics. So for the code generation, you have to traverse the AST constructed This traversal can be defined using a set of code generation functions, also known as semantic functions. Semantic functions. For example, the following code R function defines the code generation of the arithmetic expression for a virtual machine. For example, if your syntax is a number, your code R is for generating LDC number. If your syntax is plus expression, your code R will generate the left part first, and then right part, and then add. Since your virtual machine is a virtual stack machine, abstract stack machine. So in this context, you are considering a virtual machine, which is called an abstract stack machine. Okay. So for multiplication operators, just as a sub 1 plus a sub 2, your code R may generate. Similarly, code R of E sub 1, and then code R for E sub 2, and then mul, which is multiplication. So note that the arguments of the code generation functions are enclosed in double brackets. So this is just for maybe considered as a normal parenthesis for the argument in your code. But in your semantic functions, you will tell the difference of semantic domain and syntactic domain. So this means your semantic function is accepting syntactic object. So your syntactic object is enclosed using double brackets. To implement the code generation function, so we are moving from this one to the code. Just write a code, write a function accepting AST node pointers. So it is very easy to write that your code generation function may be void code R accepting node pointer. Okay, which is for this case, just accepting the AST, then you are traversing the AST. So let's focus on the, so do you have any questions up to here? No questions? So let's focus more deeply into the virtual machine. A virtual machine is not an abstract machine because the abstract machine, maybe it is enclosed in the abstract machine, but it behaves just like a real machine. So it is working machine. Virtual machine is working, it's runnable. A virtual machine is usually used to support code mobility, as you know. Typical examples of them include TVM and P-machine. P-machine is adopted in .NET platform. As you know, the TVM is adopted. So actually they are using different name for the P-machines. They are calling it CIN, okay? TVM is adopted Java virtual machine on Oracle platform or something. So in this laboratory, we'll use TVM. TVM is tiny virtual machine, which is a much simplified P machine. So it is a subset of P machine, and the full description of P machine is described in the famous book, of Reinhard Wilhelm, Compiler Design, which is quite old book, so you may not find this from your library. So, but don't worry, I already implemented it by extending from the original author of Soo-hyun Lee, who is the professor of Changwon University. And TVM assumes a single control stack in the memory called store. So you may consider that there is a sequence of blocks called store in TVM. And you have special registers such as stack pointer or frame pointer. Actually, the frame pointer is not described today, but it is needed for supporting function calls. So we'll just only consider the stack pointer and the store today. So it is a stack machine. For the stack machine, it is very simplified because you don't need to consider the registers. All the temporary storages is recorded, can be used in the store, in the stack. So TVM has several binary operators for integer arithmetic, such as add for addition, and sub for subtraction, mul for multiplication, and div for division. And there's no more. It is, since it is simplified. The semantics of an operator can be defined as machine components. For example, the semantics of add is defined as follows. So let's consider that you have a stack pointer here, and you are storing, then you are assuming that for the addition, you have two numbers on your store. So this may be 5, and this may be 4. Then you are considering this one. This one is left operand, and this one is right operand. So 4 plus 5 is stored on this location. So can you see that the semantics of this one is just, I'll execute it manually. This is 4, and you know that this is 5, and it is stored on the location of 4. So 9 is stored here. And you are decrementing the stack pointer. So your stack pointer is modified to point to this. This is the semantics of your abstract stack machine. Okay. Any questions up here? No questions? Okay, good. Then you are prepared to perform today's work, which is code generation. Based on the design for the abstract syntax tree, so it is preferred to start from laboratory 10. So in your laboratory 10, you may remember that you are making for an expression, for example, 1 plus 2 times 3, you are making an abstract syntax tree. For example, 1 times 2, 3. So this is the contents of your laboratory 10. Okay, so you are generating the AST from your expression. Then you are starting from this AST. So you are traversing this tree. You are traversing this tree and generate the code. So as the first step, write an abstract syntax for the following concrete syntax. So it isn't just an exercise. So you can write an abstract syntax. Okay, you can do that very simply. And note that the modular operator is discarded in the above grammar, which was included in Laboratory 10, since TVM does not support the instruction mode. So the following expression, for example, it is somewhat complicated. It is somewhat complicated. So let's start with the simpler one. So let me start this syntax. Okay. So from that syntax, you may write code R, and your argument is plus 1 times 2, 3. Am I right? Then according to your previous definition, you should generate the code R. Really? Okay, good. So your TA is available. Go back to here. So you can visit the OSPA site and then download the handout. That will be very good because you have to consult the previous page of this handout. Okay, so let me just tell all of them. Web server support, including UNESCO. So please download the handout for your reference. Okay, so let me keep going with this context. So your code R is just, so you know that this part is sub 1, and this part is a sub 2. So your code R is translating this 1, which is the part of a sub 1, and code R for times 2, 3, and then add. Okay. So for the 1, you know that it is for the load constant. Load constant 1 is generated. For this one, you have to invoke coder again for 2, and then code R for 3, then mul, which is multiplication, and your add is attached for the last instruction. Finally, your code, so let me just like this. Finally, your code is load constant 1, load constant 2, load constant 3, multiplication, and add. This is your final code for your virtual machine. Okay. So Let me be more specific for that. Any questions up here? So let me specific for that. So in your previous slide, you can visit GitHub site, which is TVM. So let me share your GitHub site. So from this site, can you see this? You can just click and download zip. So after downloading it, so this is window-based, but it should work for your MCs. So let me check that. Once it is downloaded, you can check it as TVM master.zip. So let me share this here. So it is downloaded here, TVM master.zip, and you can extract the contents of it, decompress as default. Then you can find TVM master files with make.bat here. So I'll execute make.bat from command prompt. So in your command prompt, so let me reshare this. In your command prompt, you just type make. So it is just a single source file. So it will compile it as TVM. And there's a simple T file, hello.t. So you may execute TVM hello.t. Then hello is the output. This is the output. And others are execution statistics. Okay. So do you remember the code which was written previously? So let's write down expr0.t, load constant 2, load constant 3, load constant 5, and multiplication and add. I'm not sure it is 5 or not. Add. So this is your instruction. So you may execute tvm expr0.t, but it doesn't print anything because you didn't invoke it to print it. So for the print, expr0.t, you may add out for out stack top, assuming that it is an integer, and then stop your code. So this two code is added by myself manually. So you may execute. Really? Yes. Just type expr0.t for sure. Okay. Then tvm expr0.t is printing 17, which is actually 2 plus 3 times 5, which is 17. But without it, expr0.t, so without them, you may execute the TVM. So you may try that again, do nothing, but you may execute the TVM by simulating it for the step-by-step manner. TVM minus S expr0.t. So you are taking a look, instruction list here, load constant 2, load constant 3, load constant 5, multiplication and addition. So just enter. And 2 is at the stack top. So this sharp means it is a stack pointer. So your stack pointer is 1. Program counter is 1. And I'm not using frame pointer now. Load constant 3. So 3 is loaded on the stack top. Load constant 5. 5 is loaded on the stack top. And for the multiplication, you have to multiply 3 and 5, which is resulting 15. And it is pushed on the location of just beneath of the stack top. So 15 is pushed. And for addition, so addition is not shown here because it is stopped abnormally. Okay. So in order to print all the details, you are just modifying expr0.t for out and stop. Okay. Then TVM minus s expr0.t 2, 3, 15, 17. Standard out is 17 and stop. Okay, and the execution statistics is printed out. Okay. Should I try this in your M system, It seems very awkward. So let me try that in your M system, So you TVM master. So just type, so just get the contents, make the bed. G++ is also available in your MC terminal. So TVM.cpp, std, C++11, so TVM. TVM2, maybe, just in case. So you can execute TVM2 for -s for your expr0.t. Cannot open shared object file. It seems not working in the MSys terminal. Sorry. I have to do that in the TVM2. Sorry for that. Okay, it seems fine. 2, 3, 5, 15, 17. Output is 17 and instruction. Statistics. Okay. So any questions up here? So I'll go back to your handout. So you can do the similar thing for this expression tree. So let me try a little bit of it. You may check it by yourself, but let me try a little bit of it. Code on for this tree. Know that that tree should be times minus 25 minus, which is unary minus actually. And this is binary minus 2, 3. Okay. So actually this is here. So you know that you have to traverse this for the code generation. You have to traverse this for the code generation. For this part, code on for minus unary minus 25. Okay, and others. Okay, so let me consider the code on of this. This may be code on 25 and then negation. So it is load constant, 25, negation, and dot, dot, dot. So you can find that this is the part of the generated code here. Further, so you may check it. So note that the instruction negation is the negation instruction whose semantics is defined as follows. Just negate stack top. Since it is a unary operator, the stack pointer is not changed. Based on the experiment, make a report with references. Assignment 9, you can write a report in Korean. Your report should contain the following materials. The purpose of this report in your word. And the abstract syntax. And your flex and bison input files for constructing the EST. So you may copy some part of your previous work on lab 10. So you know that you can get a hint from your lab 10. The code generation function listing with explanations. So you may write this as a separate source code and what you have learned in this laboratory. The program should read from standard input. The input consists of a single line containing an arithmetic expression. Only 4 operator symbols with parentheses with positive integers are allowed for input. Also, spaces and tabs characters may be included in the input, so your lexicon analyzer should safely skip them, and your program should print the standard output. Just print a list of TVM instructions. The following shows some sample input and output. So this is the example of the first, and this is the second example. And you may check the output according to the code generation functions. So any questions on your laboratory work? No questions? Okay, then I post the review video when it is available. I'm letting you know for the by posting the link in your platform. Okay. So thank you all of you in this semester, and just remember that there's some video lectures that are remaining. Okay. So see you next time, or in your final exam. And bye-bye. 한 학기 동안 수고하셨습니다.